Okay, we're continuing on with the probability assignment 2, and we're on question 11. We've got this part that says y and z are independent events, and that is important because that will tell you how you're going to be timesing the y and z. If it was dependent events, they could be in a quotation mark like this, quotation y and z. But when it's independent events, we know that these two are going to get separate. It's going to be p and then y in its own quotations, and p the probability of z in its own quotation. So when we're looking at these, we're going to look and say, okay, which then has the p and the y quotation and the p and the z quotation, and so here we go. We've got it. P. The only reason this one is wrong is because it has a plus, because the formula is going to be minus, right? It's going to be probability of y or z equals probability of y plus probability of z minus, and since they're independent events, probability of y separated from probability of z. Okay, so that would be another way to put it, because they're independent events. Okay, so now this one. Use the rewritten rule to find probability of z if probability y or z equals 0.68 and probability of y equals 0.41. And this is where it's going to be lots of fun. Okay, so let's go with what we have as far as the formula. We got probability of y or z equals the probability of y plus the probability of z minus the probability of y and the probability of z, because again they're independent events. Okay, so what do we know? What do we know based on this here? We know the probability of y or z is 0.68, and we know that the probability of y is 0.41. So let's put that down. Okay, we're going to bring this down. We know that this is 0.68 according to mine, right? And the probability of y, mine says, is 0.41. I don't know the probability of z yet, but I do know that this y, again, ooh, beautiful, is 0.41, and then we're going to say it's times the probability of z, right? Okay, I put these in completely separate brackets. This here goes with this. Now there's nothing more I can do here with those two, but since I have this here, we're going to do the opposite. Since this is a positive 41, if it was a negative, we have a negative sign in front of it, right? We're going to do the opposite. So we're going to minus 0.41 from both sides. I've got 0.27, and it's going to be on the positive side. These two are going to cancel each other out. We've got the equal sign, so we've got a z. I'm just going to take out the p for now. Just understand that it is a positive. So that's going to be a z. And then we got negative 0.41 times z. Well, that's going to be a negative 41z if I times those together. Okay, so that's as far broken down as I can get it right now, right? But we're gonna combine these two like terms, since they both end with z. We're gonna imagine this is a 1, right? Because one letter by itself is gonna be a 1. So 1 minus 0.41 equals, and I need a calculator for that, 1 minus 0.41 equals 0.59. 0.59 z, right? And then we've still got 0.27 on its own. Now we need to get this letter all by itself, so we're going to do the opposite. Since 0.59 times z, we need to do the opposite of the multiplication, which is division. So we're going to divide both sides to be able to get that letter by itself. Right? Let's cross that out. And we know when we do this, 0.27 divided by 0.59 is going to equal 4576. We'll just go 4576.4576. And it says it wants us to round to the nearest 2 decimals. So we're going to say it's 0.46 equals C. Okay. So that whole process right there just to get that one answer. Okay, so we type in 0.46 and then we're done with that one. Okay. Okay, so if we thought that was tricky, it gets even more. It gets more tricky. Okay, let's start with reading this very carefully for question number 12. G and H are mutually exclusive events. That says a lot right there. Because what does mutually exclusive mean? It means that when you times those two together, the answer is going to be 0. Okay, it's because they're mutually exclusive. You got to know that. So G and H is going to be 0. They already are giving us that clue. Then they give us the probability of G equals 0.5. And then the probability of H equals 0.3. Right? We got 0.5 and I've got 0.3. Okay, now let's go. Explain why the following statement must be false. The probability of H given G equals 0.4. Okay, so the events are mutually exclusive, which means probability of H and G equals 0. Therefore, probability of H given G is going to equal 0. It's mutually exclusive. It's got to equal 0. Oh, it's fading out again. Okay, so we know that that's got to be the statement that's true. We've got to remember to read everything carefully. That mutually exclusive is key. Okay, now we're going to go to B. Okay, find the probability of H or G. Okay, so now we have to think formula again. Okay, we're going to go back to the formula. Let's do this. Probability of H or G. Probability of H or G. And I don't know, for me it's helpful to write out the whole formula. You may not want to. Plus probability of G minus probability of H and G. Now, do we have all of that? Do we have all of these already mapped out for us? If we really pay attention to that mutually exclusive, then yes, we do. So we have H. What is H for me? It's 0.3. For you, it might be something else. What is the G? It's 0.5. Minus, what is the H and G? We know, mutually exclusive. It's 0. Total all of that together, 0.3 plus 0.8, right? And then if you were to do that, it's 0.8. For me, it's 0.8. So H or G, the probability of H or G is 0.8. Okay, so you can see that I got that there. Okay, are G and H independent or dependent events? Explain. Okay, so when it comes down to it, it says G and H are dependent events because they are mutually exclusive. Whenever they're mutually exclusive, they're dependent on each other. Alright, let's move on to the next one. This is where it's going to get really fun. Let me get this to where I can see it good. Approximately 281 million people over age 5 live in the United States. Of these people, 55 million speak a language other than English at home. Of those who speak English, another language at home, 62.3% speak Spanish. So, what is the probability of those who do not speak English? Okay, so we know that there's 281,000 people in the United States, right? Over the age of 5. We know that 55 million of those people speak a language other than English. So 55 million do not speak English. How are we going to find out the probability of those who don't speak English? Well, we know that it is 55 million. What is the fraction? Over 281 million equals, and then we can divide that. Oh, let's get there. We'll bring this into focus. I'm just gonna go 281 divided by 55. Wait. Sorry, 55 divided by 281. Right. 1.957. Right? 1957. Let's see. There we go. That's how many. That's the probability of people who do not speak English. What is the probability of those who do speak English? Okay, so if we know 55 million do speak English, how many people don't speak English? Okay, so for part B, we're going to take that 281 million and we have to minus it from the 55 million that we know don't speak English to find out how many people do speak English. So let's go with that. Again, I'm taking out the zeros because the, doesn't have to do that. So it's 226 million. And how we're going to find out the probability? Well, you have to divide it by the total amount of people. So 226 divided by 281 divided by 281 equals 0.80427, and if I were to round that off to the 4 digits, it'd be 8043. Let's see. Okay, there we go. 8043. Now the probability of those who speak Spanish out of and do not speak English. Okay, so let's do this. Okay, those who don't speak English, let's see. I'm trying to think of the best way to do this. Okay, those who don't, those who, let's see, probability of S and E. Okay, equals. Okay, those who speak Spanish, let's go Spanish, equals 62.3%, or equals 0.623. And those who do not speak Spanish is 55. Oh, sorry, we figured that out already. 0.1957. Okay, so what is this supposed to be? It's supposed to be probability of S times the probability of E. So if I took the 0.623 times that by the 0.1957, we are going to come up with 0.1219, and that would be the answer for that. Okay, so we got 1.1219. I didn't use a calculator just because I already had it calculated, but basically if you times those two numbers together, the 0.623 times the 1.157 that we got from the E, which is those who speak another language at home, that's the probability of those people, right? Sorry, moving. That's how we're gonna come up with the 0.1219. Okay, now we've got this other problem. Let me erase my board. We've got S given E. S given E, which is those who speak Spanish, given that they speak another language, right? The probability of that. Okay, so how are we gonna do this? We need to have S and E over the second, which is the E. All right, let's see what we have. Do we have the S and those who speak Spanish and those who speak another language at home? Yes, we do. It's 0.1219. 1219. Okay, right? And do we have those who speak another language? And we have that as well, and it's 1957. All right. Okay, those who speak another language. Alrighty, and all we would do is divide that. So let's go to this. We have 0.1219 divided by 0.1957 equals 0.62289. Okay, let's round this off to the nearest 4. We got 6, 2, I would say 29, but it's actually going to bump it up to 6230. Alright, so that's going to be the correct answer right there. And if you see, 0.6230. Alright, let's move on to the next one. Next one. Let me erase my board. We've got number 14. Number 14, let's get rid of this calculator for now. Trying to keep my hand steady, sorry if it's a wreck. In 1994, the US government held a lottery to issue 55,000 green card permits for non-citizens to work legally in the US. What does that say? Renette Deutsch from Germany was one of approximately 6.5 million people who entered the lottery. Let G equal the one green card, whoever won a green card. Alright, so who won a green card? Let's see. Probability. Okay, what was Renette's chance of winning a green card? Write your answer as a probability statement. Okay, so we know the probability. They want to know what is the probability of the green card, right? Of winning a green card. And he is 55,000. There are only 55,000 green cards out of 6.5 million people. So that's the total population, right? So if we were to write it a fraction, what are the chances? Well, there's only 55,000 out of 6.5 million, or 6,500,000. And if I were to divide that, let's go. I'm just going to type this whole one in. 55,000 divided by 6500000. Alright, so we would have 0.00846, but if I were to round it off to the 4 digits, it'd be 0085. We got that? Yep, we had it. Okay, so that's basically what I was writing on this side. Let's get rid of that. Okay, next one. The next one is, let's get rid of this. In the summer of 1994, Renette received a letter stating she was one of 110,000 finalists chosen. Once the finalists were chosen, assuming that each finalist had an equal chance to win, what was Renette's chances of winning a green card? Let F equal was a finalist. Write your answer as a conditional probability statement. Okay, so F is not the winner. It is just the probability. Well, it's just that they were a finalist. Okay, so we want to know what are the chances of getting a green card if you were a finalist. Okay, how many green cards are there? And if you got a green card, were you a finalist? Were you both? You know, it's like a green card and a finalist. You know, there are only 55,000 to have been able to have a green card, and you had to have been a finalist. So we're gonna say that G and F equals 55,000. Okay, 55,000. And if we're saying F, because this is G and F, right? If we were doing that formula over F, what is F? F is, it says if you were a finalist at any time. Well, there's 110,000 that were finalists. So if you do 55,000 divided by 110,000, what are you gonna get? 55,000. 55,000. Let me get that cleared up. I can't see it. 55,000 divided by 110,000. We got 0.5. Okay, so 0.5. So we know that if you were a finalist and you got a green card, right? Given that you got a green card and you're a finalist or whatever, it's going to be 0.5. Well, no, given that you're a finalist and that you receive a green card, I should say. That you were a finalist. Here's the event. The event is you're a finalist, and then the chances of getting a green card is 0.5. And I think I tried putting 0.5 and it didn't accept it. I don't know if it will for you, but when I put in the 4 decimals, then it did. So I had to put 5,500. Okay, are G and F independent or dependent events? I put down G and F are dependent events, right? The probability of being a finalist and getting a green card and the probability of being a finalist, when multiplied together, give the probability of the green card. Okay, probability of, let's see, what was it? Of those who won a green card. Okay. I cannot honestly promise that I'm going to get those parts right. Okay. Are G and F mutually exclusive events? G and F are not mutually exclusive because you could be a finalist and also win a green card. And we also know that G and F, when we're looking at it, is 55,000. So no, couldn't be because it doesn't equal 0. Alrighty. The next one, how hard is this one? We'll do one more for this video because we're kind of running over time because those ones are a little bit more complicated. Okay, so we've got 15. Number 15. The following table of data obtained from the baseballalmanac.com shows hit information for 4 players. Suppose that one hit from the table is randomly selected. Okay, are the hit being made by Jackie Robinson and the hit being a double independent events? And the answer is no, because the probability of a hit made by Jackie Robinson, given that the hit is a double, cannot equal the probability of the hit made by Jackie Robinson. Okay, I won't even lie, I don't even understand that. But that's the answer. So okay, we'll continue on the next video for the rest.